joint distribution. So let me write it down. So what is joint distribution? So till now, whatever we have learned in all these videos, in the previous videos, right? Those were with respect to one random variable. But in real world problems, we have two or more random variables for modeling any problem, any real world situation. So how do we model when we have more than two or more than two random variables? So how do we model those? So for that, this class is there. So we'll understand about how we model two or more random variables. So what's joint distribution or joint probability distribution? This is the probability of two or more random variables occurring simultaneously. Okay, so this is the probability. This describes this value, whatever this function is there, right? So it describes the probability of two or more random variables. RV is a random variable occurring together or simultaneously. Okay, this is what it gives me. And the two random variables can come from totally different distributions. Even one can be discrete and the other can be continuous. Okay, and it will give me the joint distribution of the two random variables put together. That's what joint distribution means, that when we have that value of two random variables, what will be the combined probability of both of them occurring simultaneously. So let me write down. It is applicable. Two random variable may not come from same distribution, same or similar distribution. Even I'll be more lenient, I'll write similar distribution. And for example, one RV can be discrete and second RV can be continuous also. Even that is the case. So this is the case, even that is possible. That's what I'm saying. But when we discuss, we'll be discussing about two similar kind of random variables, similar distributions, discrete, and continuous. But this is also possible. I wanted you to know this. So let's. So for example, in real world, I'll give you a real world simple example, and then we'll see a concrete example. So a real world simple example is, for example, if you have two random variables, such as height of a person and the weight of a person. So if you want to see what is the joint distribution or combined probability of a specific height and specific weight, then we say that that this is a joint distribution of height and weight. For example, if we have a person, okay, of height 170 centimeter, and we want to find the weight of that person. So what we will do is that we'll take the weight of all the people who have 170 centimeter height, and the average of that will give me the weight for the 170 centimeter person height. Okay, so these examples will keep on coming later also. I'll discuss about these examples again, but there'll be one common example which will be running through, which we'll use throughout the this lecture to understand all the three concepts. Okay, so let me give you. So one example that I gave you, right? So what was the example that, for example, I'll write it down for you. For example, two random variables can be, like, for example, one can be height of a person x and weight of a person y. Say for example, we can model the problem anyway. Height can be Gaussian distribution, and weights I can keep as discrete or Gaussian, whatever way. But there are two random variables. If I want to have the, so joint distribution tell us the probability of person of a specific height and weight, that combination. So for example, if I want to find a weight of a combination of a person, say 170 centimeter height and 70 kg weight. So we want this combination. What is the probability of finding a person of this? This will come from my joint distribution. Okay, I hope this is clear. So let me set up the example which will be more clear. So for example, let's say we have two bags, okay, and both of the bags contain, the first bag contains 2 red balls and 3 blue balls, and the second bag that contains 3 red balls and 2 blue balls. Okay, so how is it? So there are 2 bags, one bag, second bag. So this is your, say for example, this is bag 1, this is your bag 2, and what do they have? So there are how many red balls in the first one? First one has, say for example, 2 red balls. And the second one has 3 red balls, 1, 2, and 3. And the first one has, say for example, 3 blue balls, and this has only 2 blue balls. Okay, this is my setup. And so we will model the random variables as, so this will be, if I choose, let me make it thinner. If I choose a ball from bag 1, I will model it using the random variable A, and if I choose from bag 2, I'll model it using the random variable B. So these will be my random variables. Okay, so now, so what is the question? So there are 2 bags, bag 1, bag 2. Okay, and now my statement is that a ball is randomly selected from each bag, from bag 1 and then bag 2. Okay, and both the draws are independent of each other. Okay, a ball is randomly drawn from each bag, okay, such that both draws are independent. That is the case, right? That will be, so I'm just being more explicit, independent of each other. So we have this case, so both the draws are independent of each other, and then whatever I mentioned here, right? So let me write that. So let A and B be the discrete random variable. So let A and B be discrete random variable associated with outcome of the draw from first and second bag respectively, of the outcome of the draw, which color ball is drawn from the first bag, draw from first and second bag respectively. So whatever I have drawn here, I have written these in words. So bag 1 contains 5 balls, bag 2 also contains 5 balls. One has 2 red balls. First one has 2 red balls, 3 blue balls, 3 red balls, 2 blue balls. So if I draw a ball from bag 1, so that is modeled using random variable A, and if I draw a ball from bag 2, I'm using a discrete random variable B for drawing the for modeling the problem. So let's see what will be the probable solutions. So let's draw this out. So this will be simple. So let me draw. So either it can be, so let me draw this way first. Okay, so either A can have a red ball or B can have red ball, and then B can have a blue ball or A can have a blue ball. So there are 2 draws, right? So this is 2 draws. First draw is for A and the second draw is for B. So either the first one has a red ball and the second also has a red ball, first has a blue and the second has blue, and all the four combinations: red red, red blue, red blue, blue blue. So these are four combinations, and let's write down the probability of each of them. So what will be the probability of, so let's focus here. So I have to write, so both the variables are independent. So what will be the probability of, what will come in this column? Sorry. So this is the, this is my setup. So I have drawn this. So this gives me all the four combinations in the tabular format. So what will be the probability that I'll get here? That the probability of drawing a red ball in the first row and a red ball in the second row. This is what this cell will give me, right? So this will give me the joint probability of a red ball in the first row and a red ball in the second row. This is a joint probability. Each cell will give me the joint probability of that combination. So what is the probability here? So let's write it down. So let me write it down using this color. Okay. So this can be, what will be the probability of drawing a red ball in the first row? So this is coming from the first bag. That will be 2 out of 5. So this will be 2 by 5 into, both are independent. So the joint probability will be multiplication of both. And what will be the probability of drawing a red ball from this bag too? There are 3 red balls out of 5. So this will be 3 by 5. So what is the total probability? 6 by 25. And this is our, this is nothing but our joint probability. Okay. Similarly, all the combinations will have the joint probability. A red ball and a blue ball in the first and red ball in the second, and blue ball in the first and blue ball in the second. All these columns, all these cells, each cell, there are 4 cells, right? So let me make this also here. All these 4 cells will give me the 4 probability distributions. I hope that is clear. And this each cell value is the joint distribution. Okay, so let's quickly fill this up so that you know. So let's calculate all the 4 probability distributions, and then I'll give you the property also. So now quickly, what is the distribution here? Getting a blue in the first draw, that is 3 by 5, and getting a red in the second draw is 3 by 5. This is equal to 9 by 25. Okay. Then getting a red in the first draw is 2 by 5 into getting a blue in the second draw is 2 by 5. That is equal to 4 by 25. Okay. And then let's say from here. So now we have blue in first row. So that is again 3 by 5. 3 by 5 into a blue in the second row. So here it will be 2 by 5. So this is equal to 3 to the 6 by 25. So these 4 values are my joint distributions. 6 by 25, 9 by 25, 4 by 25, 6 by 25. And there's an important thing. If you sum up, okay, sum up all these distributions, all these joint distributions, right? They should sum up to 1. That's the required property. It should sum up to 1. And let's see if it sums up to 1 or not. So the combined total joint probability is equal to 6 by 25 plus 9 by 25 plus 4 by 25 plus 6 by 25. Let's see. 6 plus 9, 15 plus 4, 9, 19 plus 6, 25. This is equal to 25 by 25. This is equal to 1. So this satisfies. So hence this is holds the property for a joint distribution, that all of it should sum up to 1. I hope joint distribution is clear. So let me formulate it, right? Give you some formula so that you remember. Okay. Now, so again we'll define the CDF, PMF and PDF. Okay, so what will be the CDF? Joint CDF. Joint CDF, what will be the formula? How do we give this? So joint CDF is given by, how is the formula? X comma y. This means x and y. Okay, the CDF of x and y. So if I have variables, there are some books which gives a and b. I'll make you familiar with these notations. They use x, y, a, b. So I'll give you a, b notation also, and then later on I'll use x, y notation itself. Okay, so I'm just making you familiar with the different notations so that you don't get confused when you see these notations. Okay, what is this? Probability of x less than or equal to a, and when we comma is read as and. Wherever you see comma, read it as and. Okay, and y is less than or equal to b. Okay, where minus infinity, a and b lie between minus infinity and plus infinity. So this is your joint CDF. And what will be the for the discrete case? For the discrete case, what will be the value be? Same thing. How will we write it? F of x comma y, x and y, a and b. I'm using this a and b now, and later on I'll use x and y. I'll come back to the x and y notation. It is just to make you familiar. Only here I'll use it. So again, this will be probability of x. I'll write it so many times so that you remember it. So this is what it is. Probability of all the values. This is cumulative, right? Remember CDF. This is cumulative distribution function. Is summation, a running sum of all the probabilities till a, of all the values of x till a. So we sum it up, and y will be less than or equal to b. What will be the value? How we write? So xi less than or equal to a, and summation yj. I will write it as, I'll use another variable, yj less than or equal to b, and then we do probability of x is equal to xi, comma y is equal to yj. Okay, so this will sum up for all the values less than or equal to a. So xi will run from whatever values a can miss, x can take from minus infinity till a. Okay, so what will be the continuous case? Similarly, so here if you see the joint probability is again the summation of both of them. This is a product of this and this, comma is read as and, probability of this and this, that is the joint probability. What is the continuous case? So just make you familiar with the terminologies. Capital F is used for the CDF. I hope you remember that from the CDF field. A comma b is equal to, again I'll write the notation, less than or equal to a, y less than or equal to b. This is equal to, what will be? This is summation. Here you use probability p, and for PDF density function, this is for discrete case, right? So for this continuous case, this will be written as minus infinity to a, minus infinity to b less than or equal to, and then f of x comma y, small f. Okay, and we integrate for both dy and dx. So this small f is for the, this will denote, this denotes my PDF, this is my PMF. Okay, so for again, so there is one more thing, let me write it down. So the properties, here, so this is also called, this is the, so let me write it down in the PMF form only. So let it be here, let it go back. So let me write down as a joint PMF. So again, let's write down the joint PMF itself. This is for the discrete case. What will be the joint PMF? Write it again for the discrete case, countable case, discrete case. The formula will be probability of x comma y is equal to probability of x is equal to x. Okay, So PMF is at a particular point. CDF is the cumulative. This is the running sum. It is sum of all the values. PMF is at a particular point because we have these points, right? Remember that. So x equal to x and y is equal to y. This is equal to probability of x is equal to x, comma, y is equal to y. And do you remember the properties that it should hold? So what are the properties? It should be, so given that, such that probability of x is equal to x, comma, y is equal to y, that both the conditions hold, is greater than or equal to 0 for all pairs of x, comma, y. And the second condition is all of the probabilities should be positive. That's the property of the probability itself. And the sum of all the probabilities should sum up to 1. So what will be the summation? Sigma I, sigma j, and then probability of x is equal to xi, comma, y is equal to yj. This should sum up to 1 because the max total probability is 1. All these should add up to 1. So I hope joint PMF is clear. So this is notation, and this is what the example that we discussed here, right? So this is a discrete case only. Okay, so let me write down the joint PDF also. Let's come down. So it will be the let me use the black one. What will be the joint PDF? With the joint PDF. So this is for the continuous case. Let me write that down. And continuous case. And here the donation. How do we donate this? Denote f of x y, x comma y for x comma y. This is my PDF. Okay. And generally this is equal to like we give a, okay, simple form, f of x comma y, x comma y, dy dx. So this x belongs to 2 dimensions. This notations and all you will be clear. This means that r of 2 dimensions. Okay, that is x and y dimension. This is for the real number of 2 dimensions. This 2 means that. And r simple means this is 1 dimension. And r of n means n dimensions. R of d, we will come a lot around that. So when I discuss about the vector algebra, then I will discuss in detail about this. Okay, but generally there is a quick thing that this joint distribution maps from 2 dimensions to 1 dimension. Okay, just good to know. Don't worry, you'll get familiar with these notations later. Okay, and there's one more thing about PMF. What is the PMF? It is the derivative of the CDF, cumulative distribution function. So we'll write that in that way also. F of x comma y, xy, this is equal to the second. So we'll differentiate it with respect to both y and x. Okay, and what we'll differentiate the CDF. This is my CDF and this is my PDF. And if you don't understand these notations, so we'll discuss this during the calculus. This is partial derivative with respect to y and then partial derivative with respect to x. So once we differentiate this CDF with respect to y, keeping x as constant, and then we differentiate this function CDF with respect to x, keeping y as constant. So this is called partial derivatives, when one variable is counted and the second one remains constant. Okay, so I'll put those links, all the calculus video links, in the description. So I hope this joint probability is clear. So even these will have the properties. So let me write the properties, similar properties. What will be the properties for this? All these properties are coming from the past itself. So I'm just revising it so that you remember. So the first property would be same thing, that probability for any given range, right, for xy is always greater than 0 for all combination of xy, and the summation would be 1. Sum of all the area under the curve of joint PDF would be, joint probability distribution would be 1. So we'll integrate from minus infinity to infinity, both the variables x and y, and this whole thing should sum up to 1 dy and dx. This is should be equal to 1. So I hope the joint probability distribution is clear.